Hello and welcome back. Today we are going to look at the next topic, which is essentially about entropy. So we'll start off this topic by looking at what is called as Clausius's inequality. So let's see what that is. So we know that, for example, when we run a Carnot engine, what we know is that if we take the ratios of the heat transfers and the temperatures, we know that this is the case. So if I have a Carnot engine over here, it's a reversible engine, it's running in a cycle. If I have the reservoirs at temperatures of TH and TL, and if I have the heat transferred as QH and QL, then we know that this is true. QH by TH is equal to QL by TL. So this is true when we are taking the absolute values of QH and QL. So we know that for this engine, QH is positive, QL is negative, heat coming in, heat going out. TH and TL are in Kelvin scale, so they are always positive. So taking the magnitudes, we know that this is true. But if we take with the signs, then what we know is QH is positive and QL is negative. That's something we know. But when you're writing it, what we mean is, if you take magnitudes, this is correct. So what Clausius said is that he said if you take the cyclic integral of del Q by T, he said that the cyclic integral will be always less than or equal to 0. So we can actually see a proof of this. So for example, if we look at, say, a reversible engine, so which is, for example, this is a Carnot engine, it's a reversible engine, it's taking in QH, giving out QL and giving out amount of work as W. Then the cyclic integral of del Q by T, we can see what it is. This is a Carnot cycle. So a Carnot cycle has, for example, it has two isothermal processes, two adiabatic processes. In the isothermal processes, we have heat transferred, and in the reversible adiabatic processes, because it's adiabatic, there is no heat transfer. So in the adiabatic processes, which are 2, 3 and 4 to 1, we see that there is no heat transferred. So we don't have to worry about them because Q for those processes is 0. For the isothermal processes, the heat transferred is in 1 to 2 and 3 to 4. And the amount of heat transferred in, for example, 3 to 4 is QH, and in 1 to 2 is QL. So what we, and it's an isothermal process, so the temperature is constant. So this is TH and this is QL. So we can, for a reversible engine undergoing a process which is cyclic, we can expand this as essentially sigma del Q by T for the two isothermal processes, and this is essentially QH by TH plus QL by TL in terms of the correct expansion is just QH by TH plus QL by TL. But in this case, what we know is that QH is heat entering this system, which is positive. Over here, QL is heat leaving the system, which is negative. So the way we have generally been writing is, if I, for example, write the first law for this system, the first law for a cyclic process says cyclic integral of del Q is cyclic integral of del W, or sigma del Q is sigma del W. So the work done over here in this process is essentially sum of the heats transferred is QH by QL, where we know that QH is positive and QL is negative. But for our convenience, since we always know that this is positive and this is negative, we have also been often writing it as this. We have explicitly been putting the mod signs sometimes. In most textbooks you do not see these signs, but they just write QH minus QL, where they say that the magnitudes are what we are taking into account because the sign is already put ahead. But the general form is this, where QH is positive and QL is negative. We know QH by TH is QL by TL. We know this from Carnot. Therefore, this is a positive quantity which is equal to this, and this is a negative quantity. So, therefore, this would be equal to 0 for a reversible engine. We can show the same also for a heat pump, where we have a reversible heat pump where we have a similar kind of expression, and we see the same kind of thing. Over here, of course, if I just look at sigma of del Q, sigma del Q is QH plus QL, where QH would be positive, QL will be negative. So, this will be actually a difference. This is greater than this because we are doing some work, and this will also be this will be greater than 0. I mean, just that is for any heat engine. For any heat engine, you give more heat, you reject less heat. This is greater than 0, but for reversible heat engine, we see that this sigma of del Q by T or cyclic integral of del Q by T is essentially 0. For a reversible heat pump, we can look at the same kind of a thing. If I was to run a reversible heat pump here, I am transferring heat from a reservoir which is at low temperature to some high temperature. I take QL of heat here, give some QH of heat here. In order to do this, the second law says I need to do some amount of work which we call as W. This is reversible and runs in a cyclic process. So, the first law for this would be, it's a cyclic process, it will be given again as cyclic integral of del Q, cyclic integral of del W. Any cyclic integral of energy would be 0 because that is a property, and cyclic integrals of properties are 0. So, this tells us that del Q, sigma del Q is sigma del W. So, it tells us that QH plus QL is equal to W. Our sign convention is that energy entering this system is positive in terms of heat, energy leaving in terms of heat is negative. So, over here QL would be positive, QH would be negative, W would be negative because it is work being done on the system. So, this is what we would get. So, what we can do is multiply all of them by a negative sign so that we get W as positive, then we get this as negative and this as positive. And what we often do in textbooks is that we write the positive value of W is equal to QH minus QL. So, that is how it is often written in books, but this is the usual form. In this form, we need to take into account the sign conventions. Here we write this after taking into account all the sign conventions. Knowing that work is done on the system, we say the amount of work being done on the system is essentially a numerical value of this minus the numerical value of this, which is also what we have generally been writing. I have generally been writing mod signs in some of these places so that we know that the signs have already been taken into account. Most textbooks do not write this, but they tell you somewhere that from now on we have shifted to this convention, and if you miss that, you are likely to be a little confused. So, if you look at the cyclic integral of del Q by T ref, again this is running on a Carnot cycle. The cycle is similar to this, but only thing is we are now running in a refrigeration cycle. So, what we are doing is we are running, okay, so we have a cycle of this form. Only thing is the cycle is now in the other direction because we are providing the work. We have a cycle like this. So, again 1 to 2 and 3 to 4 are adiabatic processes, reversible adiabatic processes. There is no heat transferred in adiabatic processes, so we do not have to worry about del Q in those processes. Heat is transferred only in the isothermal processes, which is 1 to 4 to 1 and 2 to 3. So, those are the ones we need to worry about. So, in the process 4 to 1, there is expansion of the volume. In the process 2 to 3, there is contraction of the volume. So, in the process 2 to 3, we are at higher temperature and we are rejecting heat, which is QH. So, and it is happening at a temperature TH, and at 4 to 1, we are expanding the volume by getting in heat, which is essentially QL at a temperature of TL. So, what we see over here is that this QH for this system is essentially a negative quantity. It is heat leaving the system. QL is a positive quantity, it is heat entering the system. TH and TL are an absolute temperature scale. Temperatures are always positive, always greater than 0. And we know that numerically this is true. So, the value of QH, the magnitude of QH divided by magnitude of TH is equal to magnitude of QL divided by magnitude of TL. So, we have a positive quantity here and a negative quantity, both of which have the same numerical values. Therefore, when we sum this up, we get this as 0. So, what we see is that cyclic integral, so from here and here, we see the cyclic integral of del Q by T for a reversible process is essentially equal to 0. So, we have proved half of this inequality. So, we see that for a reversible process, this cyclic integral is 0. We can now see what happens for an irreversible process. We discussed that irreversibilities in a process occur because of friction or because of unrestrained expansion or because of heat transfer through a finite temperature difference and so on. So, we will see what happens to this cyclic integral for an irreversible process. So, let us consider the cyclic integral again, but now let us consider an irreversible engine. We will also consider a reversible engine for comparison. So, we have temperature reservoirs both at TH. Let us give the same amount of heat to both the engines. This is a reversible engine. It produces W amount of work and rejects QL amount of heat. We have temperature reservoirs which are the same, TL. This is an irreversible engine. By Carnot's theorem, we know that no engine is as efficient as a reversible engine. So, therefore, the work which this engine gives, if I give it the same amount of heat, the work which this gives must be less than the work which this gives. So, from Carnot's theorem, we know that W irreversible must be less than W reversible for the same input amount of heat. From first law, whatever is coming here partly goes here and partly goes here. Whatever is coming here partly goes here and partly goes here. The top, whatever is coming is the same in both the sides. So, if more of the stuff is going here as W reversible, less must be going here, and if less is going as work, more must be going here. So, from the first law, what we can see is that essentially QL must be less than QL irreversible, or essentially the amount of heat we are rejecting in the irreversible process is greater than QL, same thing written in this form. So, because we are getting less work here and we are giving the same amount of heat input, we must be rejecting more amount of heat. That is what we see from the first law. So, if we now write the cyclic integral of del Q by T, this is essentially QH by TH plus QL by TL for the irreversible cycle. This is QL irreversible by TL. If it was a reversible cycle, it would be QH by TH plus QL by TL. So, what we see is this term QH by TH. For the reversible cycle, we can also write this as QL by TL, which is what we were doing earlier. So, what I can do is for the reversible cycle, QH by TH in terms of magnitude is equal to QL by TL. For this other cycle, it is QL irreversible by TL, or maybe the other way is also it's okay. So, I still have it as QH by TH by TH. Now, QH by TH plus QL by TL is 0, and now I have, if I consider heat engines, what I have is that this QL is essentially, these are negative terms because this is heat being lost. This term is positive. So, this term, this positive term from the previous expression we had is equal to QL by TL. Now, instead of subtracting, if I had subtracted QL by TL, this would have been equal to 0. Instead of subtracting QL by TL, I am subtracting something which is greater than QL by TL. So, if I had QH by TH, if I subtracted QL by TL, this would be 0. But instead of subtracting QL by TL, I am subtracting some value, this value, which is greater than this. So, I am subtracting a larger value. Therefore, what I will get is a term which is less than 0. So, what I see is for this irreversible cycle, I get the cyclic integral of del Q by T as less than 0. We can also show this for a heat pump, which I will maybe skip because I have shown all of these already. You can do it in the same fashion for a heat pump as well. So, essentially if we put all of this information together, what we see is that for reversible cycles, we get cyclic integral of del Q by T as 0. For irreversible cycles, we get cyclic integral of del Q by T is less than 0, and if we combine both of them, we see that generally for any cycle, the cyclic integral of del Q by T must be less than or equal to 0, which is essentially called as Clausius's inequality. So, this is essentially something which we see.